We can see
All
you,
right.
but
So
the
let's
picture
go
quality
ahead
is
and
not the best.
let me move in the camera. This camera. Let me when I move the camera, this thing is self-focusing. So when I move in the camera, and we only have to deal with this for a couple of weeks. So you should be seeing the syllabus right now, and you're able to zoom in on that to make it a little bit bigger. So let's just kind of walk through this real quick. Again, my name is Professor Ron Singleton. You can call me Ron. You can use, if you want to contact me, you can use the university email system. But I got like 4 different emails to check, and the one that I have listed here is the one I check most often. So this is my personal email, and if you do send me anything to this email, you want to make sure that you write UC student in the subject line. I have a folder set up, a filter, and if you put UC student in the subject, in the heading, it'll go into that folder, and I'll see it quicker. Here's my office number listed, and this number that you see in red is I don't have a cell phone, but that's actually, if you're familiar with the Google Voice app, this is an app where you can basically it's my cell phone. I use it as a cell phone, so you can text this number if you need to. That's probably the quickest way to get in touch with me. If it's an emergency, or you just if I need to. You need to get a hold of me fast. That's just the best way to do it. So just text that number. I do teach at a couple different places. So just if you text that number, just identify yourself as a UC student, and then I'll get back with you pretty quick. I think everybody knows the meeting times because you're here. When we do meet face to face, we'll be in room 661 Baldwin, the engineering building. Let's see. Let's talk about the textbook. So a little bit of a story behind the textbook. I've been teaching this course for UC since 1999, and we had a textbook that we used. And actually, back at that time, the course was located on the Victory Parkway campus. And this was a shared course with myself. I taught the theory, and Mark Fassler, he taught the lab. It was really just 2 separate courses. You would get a theory grade from me and a lab grade from Mark. Well, over the years, the textbook prices, I'm sure you guys are well aware, it kept going up. And eventually, I think around 2004, I got rid of the textbook and I put everything on PowerPoint. So most of the stuff that we do when we talk about the actual PLC device is PowerPoints. And that's the reason, if you read on the website homepage, or actually the announcement, I suggested that you guys get a 3-ring binder and the 3-hole punch. I have a lot of information on the website. You can use it off the website, but I think it's better, especially when you're doing a quiz or exam, that you have it kind of in front of you. If you download the PowerPoints and download the documents and 3-hole punch them and put it in a 3-ring binder, then you pretty much have a textbook. So there is no official textbook. However, you do need to purchase a lab manual, and you need to purchase simulation software. When this course set up, connected to kind of like an industrial conveyor belt, and we would actually go in and do hands-on stuff, but we don't do it that way anymore. We use simulation software. So what you'll need to purchase is a lab manual, and you'll need the simulation software. Now, again, the lab manual, I had ordered that, I don't know, maybe I haven't ordered a lab manual in the bookstore in a couple years. The same thing that happened with the textbook happened with the lab manual, and that is the price kept going up. They kept jacking the price up. So I don't know, maybe a couple years ago, I asked the students if they would prefer I order a lab manual and they just kind of get it to the bookstore, or these lab manuals, this particular one that we use, there's a whole lot of them out there. And so we just kind of, what I have you do is just kind of get it on Amazon. And I've seen them as cheap as, I was looking on there yesterday, I've seen some as cheap as $5. So you don't need the lab manual and you don't need the simulation software until the 6th week of class. So you have time. But what I would recommend is just, as soon as you can, go ahead and grab that. There's an ISBN number listed here on the syllabus. And this number, if you, I'm going to show you a picture of the lab, which the ISBN number is a little bit different, but the one, it'll bring back the picture of the lab manual. And this particular manual has a CD with it that has the simulation software on it. So they have two lab manuals. You could buy it when they actually sold the lab manual from the bookstore. You could buy it with the CD-ROM, or you could buy it without the CD. Of course, with the CD, it was a little bit more expensive. I kind of like using the CD. You have to have the CD in a drive to use it. I know a lot of computers don't come with drives. You got to download a lot of programs, but personally, I like using the CD. So if you actually have a CD drive, you might want to get the lab manual that has a CD. It's just, I think you just have less issues with it. If you don't have a CD drive on your computer, or if you, you buy a lab manual and it doesn't come with a CD, there is a website you can go to. You can download the simulation software. I think it's between $35 and $45. I forget exactly how much it is, but it's not very expensive at all. So my point here is I was trying to save you some money. Instead of going through the bookstore, I'll just have you guys get the lab manual off the internet, and then we'll either your lab manual will have a CD, or you can download it from the website that I'll give you at some point. Now I'll show you a picture of the cover because I want to point something out with the lab manual. But let me just finish going through here. So for grades, the way the course is set up, you have categories of quizzes, you have homework, we have 4 exams, and then you have these lab or projects. Quizzes are 10%, homework 10%. There's 4 exams. Now the exams, it says there's 4 exams, but there's actually 2 written exams. You'll have exam around, I think around week 5 or 6. There'll be your exam 1, and then the other written exam is the final exam. So there's only 2 actual written exams, exam 1 and exam 4, the final exam. The final exam is not cumulative. It's only over the part of the course. Well, towards the end of the semester, we'll do some design techniques, and the final exam is only over that part of the course. I'll have more to say about that a little bit later when we get closer. But I just wanted to point out, it says there's 4 exams here. There's 2 written exams. One of the other exams will be an actual program that you'll write and you'll run for me. And then the third exam will be a project that you do. So I think that worked out pretty well over the last couple of years. I've been doing it this way, and I think students are pretty happy with that. So now the other thing is we'll take exam 1, I think, like I said, around the 5th or 6th week or somewhere around that time of the semester. But then after that, the other exams, it's going to seem like it may appear to you that we don't have enough time because you don't get that other stuff towards the end of the semester. But don't freak out or anything. There'll be plenty of time for everything. Really, the only thing you have to focus on and really, really study hard for will be exam 1 and exam 4. But again, I'll say more about that as we get closer to that time. As far as prerequisites for the course, I think in the university catalog it says that the prerequisite is circuit analysis 1, and you should have taken that course already. However, you don't really need that. It says it's a prereq for the course, but or at least it used to say it was a prereq. But the way I teach the course, you don't really, if you have it, it'll be a benefit. If you haven't had this circuits course or a similar circuits course, don't worry about it. We'll work around that. I kind of teach things as we go, and I don't think that'll be a problem. I'll let you read the course objectives and the course content. I want to switch over to this other page, and this one is the topics listed week by week. Now this is kind of important. So you'll notice here that we have it's kind of color coded. We have these blue weeks and we have these red weeks. So we have things highlighted in red. The blue weeks are the weeks that we actually meet our normal assigned schedule from the university. That is, we meet at 9:05 Monday, Wednesday, Friday for the whole semester. Well, not for the whole semester. For the first 5 weeks, we'll follow that schedule that the university gave us. So we'll meet Monday, Wednesday, Friday at 9:05, and we'll have our normal class schedule. But starting week 6 is when we start the labs. And at that point, what we'll do is we'll only meet 1 day a week. In the past, it's been on Fridays. I'm going to try something new this semester. We'll meet on Mondays. So starting February 14th, we'll meet on that Monday. And then on Wednesday and Friday, you'll work on your lab projects. And that's done at home using the simulation software. So it's usually, I mean, those are 2 hours that you'll have free, but you'll probably need a little bit more time than the 2 hours from the Monday and Friday. You'll need a little bit more time to do the labs than that, but you'll be able to, you'll have the weekend and you'll be able to get everything done. So then around week 11, if you look on 3/28, then we'll come back. The labs will be pretty much completed, and then we can focus on the last part of the course, which deals with logic simplification and programming techniques. So I kind of have the key is kind of keyed at the bottom down here. So make sure at some point, you take a look at this and understand the schedule. And then I have the holidays. Next Monday, of course, is a holiday. So that's going to kind of put us behind a little bit, but we'll get caught up. So next Monday is MLK Day. We won't meet that day, but I think that's the only holiday that we have this semester other than our spring break. So I have spring break here, and I'm sure you guys are already aware of the date for the spring break. So when we do actually meet on campus, you want to make sure that you guys bring a mask. I believe it's the policy of university, but basically I take care of my 80-year-old mom, and I don't want to bring anything home to her. So anybody have any questions over the syllabus or comments? Okay. Is my audio still okay? Is it decent?
Yeah, you're all good.
Yep,
Okay.
good here.
Great. I need feedback from you guys. So I'm going to switch over, and I want you to look at, let's see here. Here's the lab manual. Here's what it looks like. Now, the reason I want to show this is really, really important, because every semester I have a student or two make a mistake. It turns out that they make 3 books that look exactly alike. They make this lab manual, they make the textbook, and they make something called an activities manual. And if you go online and look at them, they all have this same exact cover. The only thing that's different is like right in here, where it says at the very top, it says Logic Pro PLC Lab Manual. If you just take a quick look at this picture, let's say you go to Amazon and you order this and you don't read it carefully, you could be ordering the activities manual, which you don't want, or you could be ordering the textbook, which you don't want. You want to make sure when you order it, if you use that ISBN number, it should take you to the correct document, the correct book. But if you're just looking at the cover, you want to make sure that you get the one that says Lab Manual at the top. So up here, it says Logic Pro. You want to make sure it says Lab Manual. And that's on the back of this ISBN number. If you zoom in on that, it's a little bit different from the one that I have listed on the syllabus. I don't know why that's the case, but I Googled the one on the syllabus and it brought me to this cover with the CD, which I think that's probably what you want. So again, we don't have to worry about that right now. We have a little time before we need the lab manual or the simulation software. So I will bring this back up when we get closer to that time. So if you have any questions or comments on the syllabus or the lab manual or the simulation software? Okay, well, let me have you do one thing. If you can see over here, there's a number. I want you to text that number. This is going to be the way I take attendance for at least while we're doing this online thing. So go get your cell phone, take it out, and you want to text this number. It's 513-494-6162. And in the body of the text, you want to put logic control, and you want to make sure you put your first and last name. And go ahead and send me a text right now to that number. Again, I don't have a cell phone. That's my Google app, my Google Voice number. And this is going to be the way I take attendance. You are required to be in class for these online sessions. So this will be the way that I check to make sure you're here. So go ahead and send me a text to that number right now. And then I'm going to erase it, and then we'll just kind of jump into an overview of the course. And guys, at any point, there's a thing on here where you can press a button and raise your hand. If you have a question, you can do that. But if for some reason If I'm not looking at the computer screen, if I don't see it, feel free to interrupt me. Just go ahead and ask your question, and I'll take care of that. I'll be happy to address it. So go ahead and send me a text, 494-6162. Make sure you put logic control in the text, and I need your first and last name. Go ahead and send that now. And then I want to talk about the title of the course, Logic Control. What is it about? And you probably already know just from experience that this is about automation and about using a device called a PLC. PLC stands for Programmable Logic Controller. But what about this term logic control? Why did they name the course Logic Control? So what is logic? What does it mean to control something, a machine or process? So I have my definition, or a definition, for logic and what we mean by control. So logic is getting a certain output based on a certain a set of predefined inputs. So when I say output, we're talking about electrical outputs. So logic, getting a certain output based on a set of predefined inputs. And these predefined inputs, what I mean by predefined, they're defined by something called a truth table. And we'll talk about what a truth table is and how it applies to logic. What do we mean by control? Well, to control something is you have a machine, and you can take this machine, you can turn the machine on, you can turn it off, you can speed it up, you can slow it down. There's a lot of ways you can control some kind of device or machine. But what I want to do is I want to look at the simplest control circuit that you can have. So let's talk about what that would look like. The simplest control circuit you can have. So the simplest control circuit you would have, you need at least 3 elements. You got to have some kind of power source. Now, I'm going to draw my power source like this. And if you had the circuits course, you recognize that as a voltage source, a DC voltage source or battery. And it really doesn't matter. Sometimes it's DC, sometimes it's AC, but I always use that symbol for the power source. So for any kind of control circuit, you got to have some kind of power source. It'll be AC or DC. You got to have something you want to control. Now, the thing you want to control, we call it the load. The load. So I'm just going to use a light bulb. That's a light bulb. I want to control the light bulb. Well, the simplest way, or the simplest control circuit would be to just take a switch, a simple switch, and connect it up to the light bulb as shown. And then what I can do is I can take that switch and I can close it. And when that switch is closed, basically this gap right there is full, and now current can cross the gap. Current can flow through the switch, and the light bulb lights up. So that's the simplest control circuit that you can have. But what I want to do is I want to look a little bit closer at this switch right here. Let's talk about the switch. Now, before we talk about the switch, let me ask you a question. What's the difference between a switch and a button? So we got switches. We got buttons. What's the difference between a switch and a button? Jacob.
So with a switch, it's always going to be in whatever position you leave it in. With a button, it usually returns to either default on or default off after you're done pressing it.
Okay, that's interesting. I want to explore that. That's interesting. Anybody else want to add something to that? A switch and a button. Nicholas.
I had pretty much the same thing. A switch is persistent while a button is momentary.
Okay.
Yeah.
All right. So I want to again, that turns out to be really important. He used the term momentary. We'll get into that, but here's a real basic difference. You push a button, and how do you move a switch? Well, when you move a switch, this is a conductor. look at this. So this right here, this and this piece are important. This is called a contact. And then this right here is called a pole, P-O-L-E. And basically, the most basic difference between the switch and the button is that you push a button and we say you throw a switch, like you throw a baseball. So you throw a switch. So let's look at a switch, and then we'll look at a button. So the simplest switch you can have is the one I have right here. I have a pole, and I have a contact. So what you can do, you can name this switch by the number of poles it has and the number of ways you can move the pole to touch a contact. Now I want to say that a second time because that turns out to be pretty important. The way you identify or name a switch is by looking at how many poles it has and how many ways you can move the pole or poles to touch a contact. So if I close the switch, I throw the switch this way, I have one pole, so I have a single pole, and I can only move that pole one way to touch a contact. So I would name that single pole, single throw, SPST. And if I move it to that position, if I have a certain kind of switch, you were right, it'll stay there until I open it back up. Now, I physically have to interact with the switch to either close it or open it. So we're going to call me the actor. I have to act on it. So we're going to use the word actor for whatever has to open or close the switch. So this is an SPST switch, single pole, single throw, simplest kind of control device. Now, I'm going to use for a switch, I'm going to use the term input. So this right here, that switch or button, this is going to be an input. And whatever the button is controlling, whatever is switching off or on, we're going to call that the output. So in this case, this light bulb is the output. Let me show you another switch. So I can have a switch like this. Maybe I have one where I have a wire here. I have the pole right here. And I have a wire here. So I got a contact, and I got this single common wire that I can either throw this over this way to the left and make contact with this contact, or I can throw it over here to the right and this pole makes contact with the right contact. So now I have one pole, so I have a single pole switch, but I can throw it either to the left or to the right. So it's a single pole double throw, SPDT. Or maybe I take it and I arrange it like this. Maybe I have a pole. I have another pole like that. And when you have it arranged like this, what they usually do is they put this dotted line between them. And so whatever the actor is moving the contacts here. What this line means is that when you move one, the other one moves in sync with it. So I can move this. So now I have how many poles? I have two poles. So I have a double pole, but I can only move those poles one way to touch the prospective contacts. So I have a double pole single throw. So this is kind of the name game that we'll play in the class, and that's one of the things you'll have to be able to do is to name a switch. Let's look at a button. So a button is kind of constructed a little bit differently. So what you'll have is you got your two contacts, and you got, say, wire connected to the two contacts. But instead of the pole pivoting at one point like this, they'll have the pole like this, right? And then they'll have some way that you can take that button and you can actually you can press that down. So when I press that down, right now this button is open. But if I press it down, then the pole will fill the gap, and now current can flow from the left to the right or the other way. What they do here, though, and this is the point I want to mention because somebody talked about buttons being momentary. They may or may not be momentary, but it turns out when you have a momentary button, that actually applies to what we want to do here. What they'll often do with this button is they'll have a spring. They'll put a spring here, a spring, which is actually applying an upward force on that pole. And so when you press this down, it's closed. Current can flow through the contact from one contact to the other. But when you release it, when the actor releases it, this thing is kept separated. And that's why whoever mentioned it being momentary, this is what you were talking about. But this turns out to be vitally important. So if I lay this on the table with no interaction at all, there's no actor acting on the device, then this switch is open. Or this button is open. So we would call this a normally open. That term, normally open. This is a normally open push button. A normally open push button. Now this is really important to understand, this idea of something being either normally open or normally closed. We'll talk about the normally closed thing in just a second. So the normal state of a button or a switch, or there's other devices that this applies to, is the state of that device when it's like laying on the table, you're not interacting with it at all, it's just laying there. Are those contacts open or closed? So if they're open like this, there's a spring separating the pole from the contacts, then we say it's normally open. If I wanted to, though, I can construct it like this. Maybe I have the contacts there, and I have the pole like this, and I still have the same spring down here, forcing this up that way. But now in this case, that spring is actually keeping this switch closed. If I press it, then it looks like this. And the switch is open, but when I release it, its normal state is to be closed. So if I name this, this is a normally closed push button. So an example of this would be like a doorbell. You go to the door, you push the button on the doorbell, and as long as the button is pushed, the doorbell will ring. But as soon as you release it, that spring is going to separate the contacts and the pole. The system's going to turn off. If I have it this way, this would be an example. Would be like, let's see, they have a switch like this on a refrigerator, or maybe on the door of your car that turns the interior light on. When you open your car door, there's actually the door actually, when it's closed, is actually separating the contacts from the pole. When you open the door, the switch closes, turns the interior light on, or turns the light on the inside of the refrigerator. So this idea of something being normally open and normally closed. Now, it turns out that most of the time, at least for this class, we talk about something being normally open and normally closed. It's usually, it'll be a button, but I want you to be aware that switches can also be normally open and normally closed. Most of the switches you deal with, like the light switch, you go in your house, in your living room, you turn the light switch on, that's going to be set to on or set to off, and the actor actually has to move the lever to move the pole to make or break contact, but they do have normally open and normally closed switches. But most of the time in this class, when we refer to a switch or button, if it's normally open or normally closed, it's going to be a button. If it's a switch, then that idea of being normally open or normally closed doesn't apply. And if it does, I'll make sure that you understand that it applies. Now let me pause for a second. How much time do I have? Yeah, we're doing good. Does anybody have any questions or comments they want to make? Because this is the important part of what I want to talk about today. On switches, buttons, or the idea of something being normally open or normally closed. Any questions or comments?
So the three elements of a circuit is the power source, the load or what you want to control, and the way you control it. Is that correct?
Yes. So you have a power source, you have the thing you want to control, and then you have the thing you're going to control it with, which for us right now is going to be a switch or a button. The thing you want to control, we're going to call that the load, but that's the output. And the thing that we control it would, i.e. the switch or button, we're going to call those the input or inputs. That's correct. And that's for any kind of control circuit. You got to have these three elements or you don't have a control circuit. Good point. Anybody else? Okay. Well, let's get into the logic part of it. What do we mean by logic? Now, when I say logic, I mean electrical logic. What do we mean by logic? And how can we use logic to control something? So let's talk about that. It turns out that there are three basic logic functions. Three basic logic functions. I'm going to list them on the board. I'm going to explain two of them. One is a little kind of hard to understand. I may try to explain it. I don't know. But it turns out that there is what we call AND logic. There's OR logic. And there's NOT logic. So if you remember when we first started talking about control circuits, I said the simplest control circuit you can have is a simple button or simple switch where you use that switch, that input, to turn something off or on. But what if you want something a little bit more complicated? What if you want to activate or deactivate something based on certain conditions? You want your circuit to make a decision. How would you do that? Well, what you would do is you would use a combination of these logical functions, or we'll say logical circuits for now, and you can actually set it up in the way that where you can have the electronics make a decision for you. And so these are the most basic ways that you can make those decisions. So let's look at the AND first. So with these two, the ANDs and the ORs, you got to have at least two inputs. Now remember, input for us is a switch or a button. So let me show you the simplest AND circuit you can have. It looks like this. You got to have your power source. And then for an AND, you got to have at least two switches or two buttons, and they're hooked up like this. And then you have the thing that you want to control, the light bulb. Now, so this switch right here, we're going to call this input A or switch A, and we'll call this input B or switch B. And when I'm going to use this light bulb, we're going to just use the letter X to represent the output. Now, if you had the circuits course, what kind of circuit is this? How's this connected up?
It's in series.
It's in series. So series means you got, if current is flowing in the circuit through a series circuit, the current has to first pass through switch A and then through switch B before it can get to the thing that you want to control. So you want to think about, for the rest of the semester, when we talk about AND logic, what we're really talking about is, for now, a series circuit. But remember when I gave the definition of logic, we said we had these predefined inputs. Well, how would I get this light to light? There's only one way to get the light to light up, and that's when what? Both these switches have to be what? Closed. So what you do is you make this table, and the table looks like this. On the left side of the table, you have your inputs, your switches, and then you have what you're controlling. And then you make the table, and the table, what it is just a list of all the possible combinations of the switches. Now, what I want to do here is, if a switch is closed, if it's closed, we're going to say that the logical value is true. And I'm just going to use a capital T for that. And if a switch is open, we're going to say the logical value is false. I'm going to use an F for that. So I can build this table using these T's and F's that represent a switch or button being open or closed. and it will look like this. All possible combinations for a 2-input AND circuit will look like this. So either right now we're at this state. Both switches are open, so we're here. Now, typically what we do, this is called a truth table. Typically what we do in these truth tables is we number them, and in this class, normally when you number something, you go 1, 2, 3, 4. In this class, we'll always start numbering with 0. The reason for that will be apparent later on, but we'll always start counting, not 1, 2, 3, we'll start counting with 0. So this right here is row 0. This is row 1, row 2, and row 3. And you can see here clearly that the only way to light that light bulb up, the only way is when this condition is true. Both A and B have to be closed. A and B have to be closed in order for me to get an output. So to build my truth table here, I put a T here. And for every other switch condition, I get that in the truth table. So this is the definition right here of AND logic. AND logic, and this is the simplest AND type of decision you can make. You might have known this in your car. Now I know a lot of cars have those key fobs. You don't have to put the key in the ignition. But if you have the car where you actually have to stick your key in the ignition, if you stick the key in the ignition and you open your door at the same time, you might get that ding, 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 the bell will ring. And so they have a sensor in the ignition, an actual switch in the ignition that your key touches. That's basically switch A. And the other sensor is the door. There's already a switch on the door to turn your interior light on. That's switch B. And the car thinks like this. If the ignition switch is closed and the door is open, ring the bell. That's a simple logical decision. And logic. Well, what about OR? How does that work? If I want to, I can take these switches, instead of hooking those switches in series, I can hook them up like this. I got an input here connected to my load. So that's switch A. With switch B, I'm going to put right here, like that. And now if you think about this, right now, there's no way for current to get to my load. It won't light up. But if I close switch A and switch B is open, I have a path for current. If I open A and close B, I have a path for current. Or if I close both of these, I have a path for current. The light bulb will light up. And if any switch is closed or both switches are closed, the light bulb will light up. The only time that light bulb, that output, will not get power is if both switches are open. So my truth table here, this is true, this is true, this is true. The only time that's false is right there. And that's OR logic. If you recognize this, if you had the circuits course, you'll recognize that as a parallel circuit. So anytime in this class we think of ORing something, OR logic, when I say that, just think for right now of a parallel electrical circuit. What about not? Well, that's a little hard to understand, but I'll do my best. So for not logic, we use that idea of being normally open or normally closed. So for not, what we do is the input that we use to represent not logic is a normally closed push button. So that's the one that looks like this. So we use that for not. So normally closed push button. If the button is not pressed, and we give it a value of true. Hold on a second. This is why I didn't want to explain this. The not's a little hard to understand, so I had to kind of think through the way I wanted to say this. A lot of times people skip over this part. They'll say, we'll come back to it, but I wanted to give you a way to think about it. So let me do this again. So here's my control circuit. All right, so the way to think about this. If you notice with the NOT, the AND and the OR, the NOT is the only one with one single input. The AND and OR can have, for AND and OR, you have to have at least 2 switches, but there's no limit to the number you can have. So the NOT is the only one with a single input. But the way I wanted you to think about this is, okay, so a push button. You think about that as being true and not pushed. Think about being false. And so this truth table, you'll have pushed and you'll have not pushed. And so this is my output. And basically, if the button is push, then this is like this. If you push that button, then this is going to be off. If you release the button, because it's normally closed, if you release that, then this is going to be on. So this will be false, and this will be true. But we said if a button is pushed, that we're going to call it true. And if it's not pushed, we said we're going to call it false. Damn, can't keep up with my erasing. I'm sorry. We're going to call it false. Now, this is actually called an inverter, because what the NOT does is it flips the value. I'm trying not to use terms that I haven't defined yet, but for now we'll say it flips the truth value. And this will, again, I'm almost sorry I tried to explain this. This is so much easier when we get into the actual course, because what we really do, we talk about zeros and ones. If you heard of bits and bytes and all of that, that's what we really use to do this. So it's a little bit easier to understand this circuit, not using this switch. But when we talk about the NOT circuit, they use a normally closed push button. So we'll leave that we'll leave that alone. And I want to talk about one other thing that's important. Hopefully, at least from my first 2 examples, the AND and the OR, you can see how you can get a electrical circuit to make a simple AND decision or simple OR decision based on whether you have the inputs in series or parallel. And it doesn't take too much imagination to say, well, heck, I can start hooking stuff in series and all kind of ways to make more complex decisions. But there's one problem. The problem is you need a human actor like me to push the button or close the switch. And that's not what we call automation. I want to automate this. I want to be able to turn something on and walk away from it and have the circuit make the decisions without a human actor intervening at all. So how would I do that? Well, it turns out that there's a very important device that we use called a relay. Has anybody ever heard of a relay? And if you have, what do you use relays for? Jacob, what's a relay?
It's basically a box that you can give power, and then it has a bunch of different switches in it. So when you turn on power, all the switches go at once, and then you'll make your decisions.
Exactly right. Anybody else? Okay, so let me go into, because everything we're going to talk about for the rest of the semester is based on this thing called a relay. This is so important that your quiz 1, if you know this, I think actually at 10 o'clock, As soon as this class is over, quiz 1 will be, it'll come live and you can see it. But don't do it yet, because for quiz 1, basically what it is, you're going to watch a video, and then you're going to, if you watch the video and then do the quiz, you'll get an A on it. But don't try to quiz without watching the video. But it deals with relays. Okay, so you'll see that, and also homework 1 is out there. You can look at that. But let's look at a relay before I run out of time. I think I got a couple minutes and I can do this. So a relay, real quick, there's only 2 parts to it. When you have a switch like this, so this is just a simple single pole, single throw switch. It turns out that this pole, it doesn't take much force or energy to move that at all. They'll have a little spring right here that applies a light force up. But when you move that, it doesn't take much force to move it. So what you can do is basically you can take an electromagnet. I don't know what they do in like junior high schools now, but I know I graduated a long time ago, right? And I was in school a long time ago. But I know in my science class, probably in junior high school, we made a simple electromagnet. Hopefully you've seen this before, but if not, look at it on YouTube. It's really simple to make. To make an electromagnet, all you need is a piece of metal, usually it's iron. You take a piece of iron, and you get some insulated wire, and you wrap the wire around the wire, and then you connect this up to a battery. And when you connect it up to a battery, you can basically pick up a paper clip with this. You've created a magnet. But the magnet works in the way that when you interrupt the current, the magnetic field goes away, and the paper clip will fall off. So now you have magnetism that you can control. Matter of fact, you can put a switch here. You close the switch, you magnetize this piece of metal, you can pick up things with it. You open the switch, you don't have a magnet anymore, the paper clip will fall off. It's a little bit more than that though. Do I have time? Yeah. I think I can do this in 2 minutes. In the circuits course, I don't know how long ago you guys took that, but there was this equation that talked about the resistance of wire. And I'm going to put it on the board. And I'll just real quick, this is the resistance of wire. This is the thickness of the wire, the cross-sectional area. And this is how long the wire is, that's the length. This is just a constant. This deals with the material. This is called the resistivity. So you don't have to worry about that. Really, the only reason I want you to look at that equation, if you know what number to put in here for material, if you know how long the wire is and the cross-sectional area of the wire, you can actually calculate the resistance of it. But I want you to look at the relationship between these. The relationship between the resistance of wire and the length, they're directly related. So the longer wire I have, the more resistance it's going to have. Well, the wire on this coil is really, really long. So it has a lot of resistance because it's really, really long. If you look at the relationship between the resistance of wire and how thick it is, the cross-sectional area, the relationship is they're inversely related. So the more area, or the smaller this is, let me do this the other way. The smaller this is, the higher the resistance. So not only is this really long, the wire that I have around the this cord, it's also really thin. So again, it has a high resistance. Well, if you remember from your circuits course, Ohm's law says that current is voltage over resistance of wire. If I have a really, really, really high resistance because the wire is really long and really thin, that means the current is going to be really low. So this coil right here, this electromagnet, is always a low current circuit. And what you can do is take this and put it right here. And I have my coil. Got my battery here. And I got a switch. So now when I close this, current flows in this coil. This is the coil circuit. Current flows, but since the resistance of the coil circuit is so high, this is a tiny, almost insignificant current on the order of milliamps. This magnetic field, since it doesn't take much force to move this switch here down to close it, that magnetic field, when this is energized, will actually move this down to that position. These are two separate circuits. They're not together at all. They're electrically isolated. The only interaction they have is the magnetic field pulling the pole down. But this switch right here, I can make as big as I want. So I can have a little bit of current controlling a lot of current. This is exactly what you do when you start your car. You put your key in ignition and you turn the switch. What you're turning is this one. That's a low current circuit. But the starter motor, which might need 10 amps to get the engine turning over, that's this circuit. Separate circuit. The beauty of all of this, give me just 30 more seconds and I'll be done. The beauty of all of this is you see this right here? This small switch right here, since I have such a small amount of current, the actor doesn't have to be a person. The actor can be a computer. I can take this coil, I can take this away, and maybe I have a computer over here that I hook the coil wires to, and I write a program that sends current to the coil, and it'll close to open the switch. Or maybe it's your cell phone. The actor doesn't have to be an individual down here. It can be another electrical device, and that's where the automation comes in. Now, there's nothing stopping me. You can see that this is a normally open switch, but there's nothing stopping me from putting another contact right here. So when this is not energized, I'm here. This is called my normally open contact. If I energize this, this closes. This is called my normally closed contact. And the way we represent this, and this is the last thing I'll say, I'll let you guys go. Instead of showing the switch like this, we'll show a normally open contact like this. And this normally closed contact will show like that. And then in the next class, when we have more time, we'll build those and or not logics. Instead of using switches, we'll use inputs. Will be represented by these relay contacts. Whew, sorry guys, I had to kind of rush there at the end. Anybody have any questions or comments? I think I went over a little bit. I apologize, but questions, comments, concerns, or is everybody all good?
All good here.
Okay, and Jacob, I really appreciate you turning your camera on so I can see a human face. I appreciate it. Guys, have a great rest of the day. I'll see you on Wednesday, and we'll get into some more of this stuff. So you have a good rest of the day and stay safe.
All right, thank you.
Thank you, you too.
Have a good one.
Bye. Thank you.